Good afternoon, everybody. We have an honor and pleasure today to have P Kroupa with us, who is a professor in applied cosmology at the University of Bonn and Charles University in Prague. His area of research is really wonderful because, as you read in the abstract of the talk, he is eventually questioning the need to revoke, to assume the existence of dark matter. He finds ways of bypassing this hypothesis. And as you may learn from internet, Pavel's CV is equally rich. He was born in the Czech Republic. Then he moved to Australia, and well, on the way there were some other stations, but finally he studied physics in Perth, in Australia, then made a PhD in Cambridge. Then he is a professor in Bonn and in Prague. And please have a look at the CV. It's really very interesting, very exciting references to his publications. Now, we just agreed that questions should be postponed to the end of the talk. Maybe not during the talk. That is much better organized. Okay. Thank you so much, Pavel. The floor is yours.
Okay, so thank you very much. It's a great pleasure to be here. The topic I'm talking about is very, very controversial, as you can imagine. So I just want to convey to you the message that the astronomical data indicates rather very convincingly that there is no dark matter. This does not mean that I'm against dark matter. I should want to emphasize that the existence of dark matter is a very reasonable hypothesis. It's but a hypothesis which can be tested against data, and that's what we have been doing, and it turns out to be rather problematical. So this is what I want to convey to you. Here's a list of papers, just in case somebody would like to check up on some of the arguments. It's not. So can you understand me? Yes? Okay, good. So what I'm talking about today is based on this literature. And so I want to start now with the arguments. One should first of all note that the standard model of particle physics doesn't provide any path for additional dark matter, any additional particles beyond those which we know about from the standard model of particle physics, which is based on quarks and leptons and the radiating bosons. Yeah? So that's an important point. None of the experiments so far has found anything beyond the standard model of particle physics, nothing convincing which indicates there is a realm of particles beyond what we today can describe more or less well with the standard model of particle physics. The LHC constrains the extension of the standard model of particle physics, in particular supersymmetry, which would contain dark matter particles, but like this quote here, the beautiful theoretical ideas underlying supersymmetry have not been seen in nature, at least not in the simplest form. So there's no actual evidence for anything beyond the standard model of particle physics, even in terms of a theoretical description like supersymmetry. It's very important to realize that the only argument for dark matter is the astronomical data. That's basically based on extrapolation of an empirical law, the law of gravitation, by many orders of magnitude beyond the realm in which it was actually derived. It was derived on the scale of the solar system. By the time of Einstein, this hadn't changed. 1916, galaxies had not actually been understood to be what they are. So Einstein's work is based on an empirical knowledge which constrains the law of gravity, which is based only on the scales of the solar system. And so when one, after 1916, applied Einstein's field equations to the scale of galaxies and to the cosmological scale, that application constitutes an extrapolation of an empirical law, essentially, by many, many orders of magnitude. Okay, that is extremely important to realize. And failure of this extrapolation by many orders of magnitude. That then is the reason why one invokes dark matter, because one hopes to avoid this failure of the extrapolation by adding new matter. So that was a very reasonable hypothesis, a very sensible procedure, because we had a well-behaved law of gravitation, the classical limit being linear and everything, so forces can be nicely added. It's actually computationally very, very convenient. And so one wanted to try, the first try is to just add additional matter, yeah, and so that can be tested. And so I just want to re-emphasize that if it had not been for post-Einsteinian astronomy dynamics observations on galaxy and larger scales, remember that by the time Einstein developed his theory, galaxies had not been discovered as such. They were nebulae, but nobody knew about the scales or what those objects were. Not even the distances in our galaxy was known. Yeah? So the only reliable data one had was the motion of the planets, basically. So if it had not been for the post-Einsteinian astronomy dynamics observations, we would simply not know about dark matter, because there's nothing else in nature which indicates the existence of dark matter. And so the arguments for dark matter are largely based on this well-developed Einsteinian theory of gravitation, which is believed by the majority to be correct. So if we take this as the basis of our interpretation, we have no option but to introduce dark matter. There is no other possibility. And so then, and observation evidence are how matter behaves, so how is matter moving on the scales of galaxies, around galaxies, galaxies among each other, as well as the dynamics of the universe are all arguments, which is what this says, which suggests there is something missing, and that missing can potentially be additional dark matter. So based on this first statement here, as a hypothesis, we say Einstein is correct on all scales. Then one can develop the standard model of cosmology. So it's based on two main assumptions. First is Einstein is valid. And then the other one, and that is actually a very important assumption, that all matter is created at the Big Bang. So after that, no additional matter comes into being. And with these two main assumptions, one can build this model, which is based on, well, this is a cartoon, so it's something like an explosion. Then the universe expands, the structures form, and today we observe the galaxies within them. And so this model is based on three additional physical hypotheses. These are auxiliary hypotheses which have to be added based on the first two hypotheses, which are these two. These are the foundational hypotheses, and these are auxiliary hypotheses which have to be added, otherwise it doesn't work. And the one is inflation. In order to introduce that the universe seems to be so flat and homogeneous, despite its initial origin as a point-like object, then one needs to introduce this dark matter, and in addition to that, dark energy, which suggests that the universe is now again expanding more quickly. So three unknown physical processes have to be introduced based on these two assumptions. Okay, so that's quite a valid scientific procedure, as long as one understands that these are hypotheses which can then be tested against data to be falsified. Verification is nice, but verification doesn't prove a theory, right? So that's how we progress. And so this model now tells us, according to that model construction, that 70% of the energy content of the universe is this dark energy, which is currently not understood. Then 25% is dark matter, and 5% is what we call normal matter. Now, of those 5% which should be in the universe, only less than half has been discovered. In fact, This is one missing baryon problem, that we can't actually find observationally where most of the normal matter which should have been produced actually is. It's believed, it's thought to be between galaxies in some sort of plasma form, so it can't be easily observed, but fact is we don't know where most of the normal matter is. So basically we have the idea is that we can only observe something like 98% of the energy content of the universe is gone missing or is not understood, or is based on physical ideas which are not understood. So uncomfortable in this construction is that the dark matter particles are not part of the standard model of particle physics, and that the dark matter particles have not been found. Okay, that's uncomfortable. It doesn't disqualify the theory, it only makes it uncomfortable. It would have been nice to find the dark matter particles. Evidence which now actually show that dark matter does not exist, but therefore the model is not correct, are all of these, and I shall talk basically about this test. Dynamical friction due to the dark matter halos that should exist in the above theory is not detected. This is the crucial one big line of testing for this theory to check whether dark matter exists. It is extremely cheap. We don't need big colliders. We don't need any expensive machinery. This test is very, very simple, and this is what I will be applying. Related to this test are all these other points. I don't want to go through them now in detail. I'll just cover them in the talk, and you should hopefully understand the arguments. And so I just wanted to, before I come to explaining what dynamical friction is, just make this particular statement. We have to realize that if dark matter particles do not exist, then the standard model of cosmology, the SMOC, falls apart entirely, and we have perhaps the largest scientific and sociological crisis in physics ever in history, because until now it has never been the situation that we had so many educated scientists working together on such a problem, thousands and thousands in fact, who have all gone so wrong. Yeah, that's... Sorry? You could also question Newtonian. Of course. Well, that's, of course, what is being done here, right? Newtonian dynamics is the classical form of gravitation.
But any physics theory can be questioned.
Exactly, yeah. So I'm just building this up because as the majority of colleagues are convinced there is dark matter, and this is the reason, yeah? Because if there is no dark matter, we do have a major crisis. Basically, we don't have a cosmological theory. So the standard model of cosmology is invalid if there's no dark matter. That means we would not know if there was a Big Bang. We would not know whether the expansion of the universe is what it's supposed to be, and so on. Yeah, that's basically the idea. I think that's a... Yeah, but maybe we should just allow discussion. If the time limit is not too critical, yeah, that's... I mean, if people are eager to ask, maybe we should. So what was the question?
So do you insist on saying that dark matter has to be in form of particles?
Well, if dark matter is not in the form of particles, it's some sort of fluid or something, then this is still true. Because then the cosmological model is not valid. You'd have to develop a completely new model based on the dynamics of that fluid. Yeah? Okay, so this is now the direct test for dark matter particles, because the current cosmological model is based on dark matter being a particle, and if it's not a particle, then that model is not valid in any case, and we'd have to start from scratch also. So this is Chandrasekhar dynamical friction. This is an extremely well-known process in physics, and it works as this. So we have here a galaxy which is moving through many dark matter particles. So we have a galaxy, it's surrounded by a dark matter halo, and another galaxy is moving through this dark matter halo made of particles. What happens is that each dark matter particle is deflected by this gravitating object. And that's why we have an overdensity behind this object. Yeah? So this is basically a transfer of momentum from the motion of this massive body to to the motion of the lower mass body. So this is nothing particularly dramatic. This can be very well calculated. So we have here our satellite galaxy, and its gravitation interacting with a dark matter particle which comes along this trajectory is deflected and then moves out. There's no transfer of energy. It's an elastic encounter, but there's a change of motion of the dark matter particle. Yeah? So this deflection can be calculated. These are just Kepler orbits, conic sections. So we can calculate here this component and that component of the velocity vector given the initial velocity vector. Then we have to integrate over all these encounters. So you have a galaxy moving through a lot of dark matter particles, and each of them gets deflected, so we have to integrate over all these encounters. We have to sum up all these effects, and it turns out that these vector components cancel out because the encounters are symmetric. Dark matter particles come from that side and from that side and from every other side. So the galaxy does not begin to deviate in any direction, just keeps moving straight. But you can see that this the deflection adds up because every dark matter particle is deflected, so the component of its original velocity in that direction is reduced. And that leads to dynamical friction. So the integration over all possible encounters is done. That's what Chandrasekhar did. And that's the equation. So we have the acceleration of the galaxy as it's moving through a dark matter halo with this density of particles, and that's the mass of each dark matter particle, and that's the velocity of the galaxy. That's just g, the gravitational constant. That's the mass of the galaxy. It's the mass of the dark matter particle. And the important thing here is that it depends on the mass density here of the dark matter particles, which means, and that is fixed by the cosmological model. That's not a quantity we can change. It's not an open parameter. Okay, that's given by the cosmology. And so we can now calculate, given this deceleration, how the torque acts on the orbit. So you have a galaxy coming in through the dark matter halo, and the dynamical friction is decelerating, so it's getting slower, which is a torque, and that leads to a decrease of the orbital angular momentum of this galaxy. And that can be calculated. That's the angular orbital momentum decreases through this dynamical friction force, because this mass of the galaxy times the acceleration from the dynamical friction. And so we can calculate how the orbit decays as a loss of angular momentum because of this dynamical friction. And this leads to this decay time. So if we start our galaxy at this distance, in a dark matter halo, which is characterized by a velocity dispersion, so a very massive dark matter halo, the dark matter particles have a higher velocity dispersion than a low mass dark matter halo, where the dark particles have a smaller velocity dispersion in order to be confined in a self-gravitating structure. And this time scale can now be calculated. So if I have one galaxy, another galaxy comes in, I can now estimate this analytically, how long it will take for this galaxy to orbit and shrink and merge with this galaxy. Yeah? And because of the dark matter dynamical friction. And this, galaxies merge once they approach within distances comparable to the diameters of the dark matter halos. We'll come to it in a moment. And here's just one example. A galaxy which has a total mass of 10 to the 11 solar masses. So that's the galaxy plus its dark matter halo will merge with another galaxy which dark matter halo is characterized by 200 kilometers per second velocity dispersion. That's the dark matter halo of our Milky Way. So our galaxy is sitting in a dark matter halo, and that dark matter halo is 10 to the 12 solar masses, which corresponds to the particles moving with a velocity of about 200 kilometers per second. And so such a galaxy which comes into our dark matter halo merges within 1 billion years. So it comes in, and 1 billion years later, it's at the center, merged. This is an incredibly short time, yeah? And so here is what we know about the dark matter halos from the theory. It's not like you can just adjust your dark matter halo. So we have here the galaxy M, that was the mass M before, plus, so this plus that was the mass. So this is the mass in stars and gas. And this is the dark matter halo mass from the theory, cosmological theory. So for example, a satellite, a galaxy with a mass of 3 times 10 to the 10 solar masses would have a dark matter halo weighing 10 to the 11 solar masses. Our Milky Way has a mass up here of about 6 times 10 to the 10 solar masses, and it has a dark matter halo, which is a few times 10 to the 12 solar masses. Okay, so each galaxy has this huge dark matter halo around it, and the mass of this dark matter halo comes from this curve here, and that's this mass here, the mass in dark matter. And so if we now look at our Milky Way, this is our galaxy, and this is the satellite galaxy, which is called the Large Imaginary Cloud, and this is the Small Imaginary Cloud. The Large Imaginary Cloud is now moving past our galaxy with about 200 kilometers per second at a distance of about 50,000 parsecs, 150,000 light years. And we know its velocity very well because of measurements which are very precise today. So we know how this object is moving. We know its mass. Its mass is about 3 times 10 to the 9 solar masses in stars and gas. Therefore, we know how massive its dark matter halo is, assuming dark matter exists. And so we can then read it off. 3 times 10 to the 9 is here, and our dark matter halo of that galaxy has 10 to the 11 solar masses. And so we come to the conclusion that this galaxy should have merged with the Milky Way within 1 billion years. And that's where the trouble begins, because it doesn't seem to be doing it at all. We do not see any evidence in the motion of this galaxy past our Milky Way for dynamical friction to be acting. Yeah? It could have just recently fallen in, but there's evidence that there's a huge tidal stream, a gas stream behind it that has been orbiting the Milky Way a few times, but it cannot have been doing that because of dynamical friction. We know the sizes of these dark matter halos. So for example, our galaxy, our Milky Way, has a dark matter halo which weighs a few times 10 to the 12 solar masses, about here. That's the mass of the dark matter halo of our Milky Way. And it has a radius which is something like 250 kiloparsecs. Our galaxy has a diameter of about 50 kiloparsecs. Our sun is at a distance of 8 kiloparsecs from the center. The whole disk of the galaxy has a diameter of about 50 kiloparsecs, and the size of the dark matter halo, the radius of it, is 250 kiloparsecs. And our satellite galaxy, which had a mass of 10 to the 11 solar masses, would have had a radius of its dark matter halo of some 120 or so kiloparsecs, so also being very large, much bigger than the distance to the Milky Way now. Yeah? And so dark matter halos are, in a sense, like spiders' webs. As soon as two galaxies approach each other and the dark matter halos start to overlap, they capture each other, like a spider's web catches a fly, and then they have to merge. Okay, and here's a movie, two galaxies like the our Milky Way and the Large Imaginary Clouds, and you can see how they merge. And they throw out these tidal tails because of energy and angular momentum conservation. It's exactly the same physics. If you throw a stone into water, the water flies out. That's because of energy and momentum conservation. So this is extremely well understood, and it's observed. I'll come to that later. So galaxies merge. Here are now images of real galaxies. You can see how close they are. They've been interacting. There's gas between them. These are the size of our own galaxy, and they are strongly interacting. Here's another pair which is very strongly interacting, and here is another pair which is very strongly interacting. You can see these beautiful tails and this star formation in these tails. New stars are being formed in these. And here's another case. You can see the star formation in these tails even hundreds of kiloparsecs away from these galaxies, where new little dwarf galaxies are being born because of these collisions. And now one can calculate how long does it take for them to merge. So this is this graph from these people. This is the initial distance of these four galaxies I've just shown, and this is the time. You can see this one here, this one starts at this position, moves in, has a close encounter, orbits past the galaxy, moves out again, so it goes out to large distances, comes in again, and then does it once more, and then it merges. Okay, so it passes, comes past it again, and then it merges. But the merging happens in 2 billion years, and this is a particularly positive example in the sense that the encounter started far and was grazing, so it took some time for them to merge. In this case, you see it comes in, has a close encounter at a distance of some 10 kiloparsecs, and then merges. So it came in, passed very close, went out a little bit, and then it merges. And this merging happens on a timescale of less than 500 million years. So these calculations show that such observed galaxies must be merging, falling together within a very short time, something like 2 times the time it takes to cross through the system, if there is dark matter. Now, we know already from a long time ago that the interaction, so the calculations of these encounters, these are very well understood. That is just classical physics, Newtonian dynamics, nothing else. In this limit of Einstein's theory, it's all purely Newtonian. And so we applied this method to the Milky Way. We have our galaxy, and our galaxy is satellite galaxies. The galaxies which are orbiting this, our big galaxy. And we calculated how long does it take for them to merge with the galaxy, or we turned the time around and we looked for initial conditions for these galaxies to have come towards our galaxy for us to observe where they are today. So this is this paper. The important thing is that from these dwarf galaxies which we looked at, these are very, very faint dwarf galaxies, which have their own dark matter halo, we find no tenable set of parameters. That means there is no in-full solution. So if we go backwards in time, we calculate the orbit backwards, taking into account dynamical friction, we come to a situation which is unphysical. Yeah? And we did it for these 4. So this indicates that, that there is there's no description of what we observe very close to our galaxy in terms of the motion of the objects if there is dynamical friction through the dark matter halos. We can now look at the next group. So our local group is composed of our galaxy, another big one, which is called Andromeda, and then some 3 million parsecs away is another group of galaxies. In between, there's basically nothing. And this other group is the M81 group of galaxies. And that's what it looks like. We have here one big galaxy like our Milky Way, and then we have a very substantial other this galaxy here, and this galaxy here. So we have these 4 galaxies which obviously have been interacting. This is gas. Gas is spread throughout the whole system, which means that all of these galaxies must have come close to each other at least once to spread the matter within this group. And so we can calculate, because we know the positions of these galaxies and we know their motions, we can search for initial conditions to see if there are solutions. And so this is an optical image. This is what an astronomer would have seen without radio observations, where all the gases. This is an early radio observation which tells us how the gas is distributed throughout the system, showing that there have been interactions. And previously, the last publications reported at a conference by Yun from Korea found that there were no solutions with dark matter because all of this merges far too quickly. You can't get the situation as we observe it if there is dark matter because Chandrasekhar dynamical friction forces this whole group to merge too quickly. The interesting thing is that this was only reported at a conference, but then no research paper followed. At the same time, an American group found exactly the same. They didn't find solutions with dark matter, only if they switched off dark matter. Again, that was not reported in a scientific research publication because it's a hot potato. You can see it very much in the literature that the astronomers have great difficulty writing papers where they conclude that there is no dark matter. Yeah, that's why my dramaturgy in the beginning, because it is a very sensitive issue. To argue that there is no dark matter is extremely, and also from a career point of view, it is suicidal as a young person to write papers that there should be no dark matter, right? So that's why they only left it at the conference proceedings. So we looked at this project recently. It's also a research project that's still ongoing. And we've now actually managed to write a paper, but that's because myself and Wolfgang Oehm do not need a job anymore. And so we found that there is no solution. Basically, all of these galaxies would have had to come at the same time from large distances, moved together, have maybe one encounter, and that's where we see them. And you can argue that for 2 galaxies, that's maybe not so unlikely. But to have 4 galaxies doing the same thing, instantaneously, basically organized in time, to have a close encounter, at the same time, but coming from very independent positions, that is arbitrarily unlikely. Effectively, there are no cosmological initial conditions which can explain this system. Okay, and so there are many other similar groups. We have these objects, these 1, 2, 3, 4 galaxies. This one is a foreground galaxy. This is called a Higgson compact group. Astronomers have found these amazing groups of very big galaxies are sitting just right next to each other. You can see how close they are. They've been very clearly interacting significantly, and there are many of these groups. If we calculate the chance of finding such groups, if each galaxy has a dark matter halo, for example, for this galaxy, the dark matter halo would be as big as this room, yeah, around it. And that would be the case for every other galaxy. So if there is this dark matter around these galaxies, these systems should be merging on a timescale of about 1 billion years. And yet we see many of them, and these galaxies are very old. You can see here this group, this was the same one here, but this one here, or this group, you see, or this group here. And so the lifetime of these groups is too short to be consistent with the number we observe out there. So therefore, the present-day motions and distances of Milky Way satellites, so the satellite galaxies of our galaxy, preclude them to have fallen in from a filament if they have dark matter halos, and the M81 group should not be there. So dynamical friction, so this evidence for dynamical friction is simply not there, this would then imply there would be no dark matter halos. Now, we can continue with this test, because it is such a strong conclusion. We can consider the phase-space distribution of matter. If there is dark matter, we can calculate the dynamical history of these systems, in particular how structures form in a universe, in this type of model. And so this is referred to here as the merger tree. So what happens here is, this is the beginning, that's the Big Bang. At the Big Bang, dark matter and normal matter begin to expand away from each other, but the dark matter does not interact with the baryons, which means it can immediately begin to collapse under self-gravity everywhere, making the first small dark matter halos, while the gas can cool. And the gas, therefore, needs time to cool, because it's initially very hot, until it then falls into these dark matter halos to make the first galaxies. And that's what happens here. So the dark matter halos first form after the Big Bang, and as the universe evolves and then gas cools, it falls into these dark matter halos, and first stars begin to form somewhere around here, a few 100 million years maybe after the actual Big Bang. And then these dark matter halos meet and they merge to make ever bigger galaxies until the present day. And so every galaxy in the universe, according to this model, has such a merger history. Big galaxies always only form from smaller galaxies, which form from smaller galaxies. Yeah, otherwise you wouldn't have big galaxies. So every galaxy has this very rich merger tree, and every merger tree is different to every other merger tree. It's like a fingerprint. Every galaxy has its own characteristic merger tree, which of course we cannot reproduce, we cannot calculate it because the dark matter is invisible, but we know that they all differ. Yeah? So the standard of cosmology predicts that each and every galaxy has a history of mergers, and the mergers are random, i.e. every galaxy has a different merger history. And so the satellite galaxies around big galaxies should be distributed spheroidally, because we know, we can calculate that the present-day galaxies should still have other galaxies around them which are in the process of merging and yet haven't merged. And the distribution of these is well known and is basically spheroidal. Yeah? It's triaxial, so, but it's basically spheroidal. There's no clear structure. But what we observe is that the satellite galaxies, each of which should have its own dark matter halo, that they are, and this is well known, they are not distributed spheroidally. This is a very major problem in current cosmology. So this here is our Milky Way. Its dark matter halo looks like this. It's not a smooth distribution, but it consists of all these little dark matter subhalos. These are the tiny little things which formed just after the Big Bang. They are so low mass that they haven't yet merged because the dynamical friction time scale is very long because they have a low mass. The more massive ones, they come in and they merge much more quickly. So this picture is very dynamic. All of these are constantly moving around. The more massive ones are shrinking the orbits to fall towards the center. New ones come in from outside. So this is a very dynamic picture. It's a snapshot, but we know that many of these more massive ones should have their own little galaxies. And the distribution of this structure on this scale of 250 kiloparsec, that's the size of the dark matter halo, should be spheroidal. There shouldn't be any planes or preferred angular momentum. And this is what we observe. So this is here for Andromeda. That's the next big galaxy nearby to our Milky Way. This is Andromeda disk. See, this is the scale of 250 kiloparsecs on all sides. And Andromeda has all of these satellite galaxies, which are orbiting Andromeda. And what these people here have discovered, Ibata et al. From Strasbourg, is that there is a population of these satellite galaxies which form a very thin plane which is rotating around Andromeda, like a solar system, like a planetary system, basically, in that sort of sense, as if these were planets moving around Andromeda. For our Milky Way galaxy, we have a very similar situation. Here we have our Milky Way galaxy. This is the disk of our galaxy. The sun is not at the center, but just slightly offset at about 8 kiloparsecs from the center. Again, the same scale as here, so it's 500 times 500 kiloparsec. And our galaxy has these satellite galaxies, and you can see all of this is empty. There are no satellites. All of these satellites are in a huge structure, which is very thin, and this structure is rotating. You can see it on the colors. This is blue moving towards the observer, that's you, and these are red, that's moving away from the observer. So both of these galaxies have satellite structures around them, which are very large, very thin, and are rotating. Furthermore, these are correlated. So this here is Andromeda, now seen from the top. That's the disk of Andromeda. And these are the satellites of Andromeda. Sorry, this is Andromeda, this is Milky Way, doesn't matter. So this here is now a scale of 500. So this is 1 million parsecs across and 1 million parsecs across. This here is Andromeda with its satellite galaxies, which I've just discussed in the plane, and these are the other satellite galaxies. This structure is rotating. And this is Milky Way seen from the top, and these are the satellite galaxies of the Milky Way, which is also a rotating system. And the interesting finding is that this satellite system is pointing exactly at the Milky Way, while this system is off angle. But if you look at both satellite systems, so these are two planes which are offset by about 30 degrees, both are rotating in the same sense. So the angular momentum of this whole structure is pointing in that direction, and the angular momentum of this structure is pointing in that direction, so they are more or less aligned within 30 degrees, which is, so this has an incredible amount of structure, which is very, very inconsistent with the theoretical predictions. How can the Milky Way and Andromeda satellite systems be so correlated if there are subhalos falling in individually? Because each of these little satellite galaxies should have its own dark matter halo and should have fallen in independently of all the other dark matter halos. But it seems that this dark matter halo knew about the dark matter halo up there, essentially, yeah? And this is physically impossible in that theory. Here's a paper found, published by Miller et al., published in Science last year, and they discovered that the Milky Way and Andromeda, so the two galaxies I've just discussed are not unique. The next big group, this is now the Centaurus A group, is showing exactly the same type of structure. This is the Centaurus A satellite galaxy. We have Centaurus, which is like the Milky Way. It has satellite galaxies, and those satellite galaxies are arranged in a huge plane which is rotating. So we can now calculate the probabilities. How likely is it to find such structures in the theory? So we take a number of very big simulations. So we assume the theory is correct. So dark matter is there, and how often should we find such disks of satellite systems? We can count in the simulations that have been done, and there are these simulations here, Millennium 2 and Illustris, and the probability of finding a satellite population like around the Milky Way is about this size, this amount, and around Centaurus A it's about this amount, and around Andromeda it's this amount. So if we put this together, relative to the different cosmological simulations, both are based on the same theoretical model, but are calculated with very different codes and with different, so some, like Millennium does not have star formation, but this calculation already has star formation in it. And so you can see that the likelihood of finding 3 such systems next to each other is extremely small. And this is a very conservative estimate. In reality, these probabilities are smaller because here we are only looking at the extent and the thinness of the planet. We are not, in addition, asking for it to be rotating. So we expect 3 of such disks of satellites amongst 238 million host galaxies in the theory. So we have to look at 238 such galaxies to find 3 such cases. In the real universe, instead, we see more than 3 such structures amongst the 5 closest big galaxies. Okay, so essentially this is a more than 5 sigma falsification of the theory. In terms of particle physics, 5 sigma is a magical number. This is much more than 5 sigma falsification of the theory. It is simply not possible to match what we observe close to our galaxy to the cosmological model. Yeah? And the structure of the local group of galaxies, so this, I remind you that we have this merger tree. So these mergers are independent of each other. So we can calculate the structures of these objects down here once in the present-day universe. So our Milky Way is a galaxy in here. That's the dark matter halo. And this is what we find for the whole local group. We have now here the scale of something like 3 million parsecs times 3 million parsecs. We are now looking along the line joining Andromeda and Milky Way. So we have Andromeda and Milky Way. These 2 galaxies are falling towards each other at the moment. And we are looking along the line of sight, looking at Andromeda and Milky Way. So this is here Andromeda and Milky Way. These are the satellite galaxies of Andromeda. This is of the Milky Way. And then the structure, the 3 million parsec volume around these 2 big galaxies is what we call the local group. It's a gravitational bound region in which all the galaxies are bound to these 2 galaxies, or it's a bound structure. It's not a structure which is taking part in the cosmic expansion. It's decoupled from cosmic expansion because of self-gravity. So this here is the whole local group. These are dwarf galaxies which belong to the local group, are gravitationally bound to this whole structure. What has been discovered in this publication is that this arrangement of galaxies is incredibly symmetrical and structured. It is frighteningly so. It's a frightening symmetry because what we see is that all of these regions here are completely empty. There are no galaxies in there. And the galaxies which do exist, which are not satellites of the big galaxies, are in 2 big planes. Okay, it's like the whole structure of the local group is in 2 planes. It's like a roof. All the galaxies are in these planes. The planes are only 50,000 parsecs thick, but about 3 million parsecs in extent. So we have very thin planes of galaxies. And Andromeda and Milky Way is intermediate between these 2 planes, equidistant from both planes. Yeah? So it's a very, very symmetrical structure, which is completely inconsistent with any structure formation with dark matter, because in that case, this should be a conglomerate of galaxies which has no symmetric distribution. This structure is moving like that relative to the background. So it's as if this structure, which is so symmetric, is moving like that relative to the background cosmological radiation. So the structure of the local group of galaxies is incompatible with the standard model of cosmology. It's difficult to put a number to this. It must be something like 100 sigma or so incompatible, because you'd have to somehow be able to calculate how likely would you expect all these galaxies to be in 2 thin planes, symmetrical around 2 other big galaxies. I mean, you would never find any such situation in a cosmological simulation. Beyond that, what Pawlowski and McGough had found, and then Barnick and McGough also, so we just saw this structure of the local group. the local group ends about here. If you go to larger distances, the galaxies are going away from us because it's part of the cosmic expansion. And they discovered that there is this group of galaxies, of 5 galaxies, which are racing away from this group. And this distribution is itself in a very thin plane, only about 50 kiloparsecs thick again, very linear and moving together, but on a scale of some megaparsec. You can see here, this is 1 million parsecs here. So the scale of 1 million parsecs, 3 million light years, and moving away together from the local group. This structure is, again, unseen in any cosmological simulation. It's far too organized. Furthermore, if you go backwards in time, all of these galaxies were at the same time in the local group. But the problem is that they then had, and this was about 8 billion years ago, so 8 billion years ago, something ejected these galaxies out of the local group, so they're moving, coasting along together in this thin plane with the same velocity. And the problem is that this is physically impossible because the local group is full of dark matter, and you cannot eject a galaxy out of the dark matter halo. It's like you being underwater in a pool. You take a rock and you try to throw the rock out of the water. It doesn't work. You wouldn't even get fire. The rock wouldn't even leave your hand unless you use a rocket to expel the rock from the water, right? That's just the hydrodynamical friction force, basically. Here, you'd have Chandrasekhar dynamical friction not allowing you to eject these galaxies outwards, and yet this is what we observe, as if dark matter weren't there. Yeah. And so this is called the backsplash problem. There are too many galaxies which are receding from the local group in too orderly and far too fast. This is impossible if the local group has dark matter. And so, again, we conclude that this is evidence there should be no dark matter. So the disagreements concerning tests relying on dynamical friction are consistent with each other and always and only point to dynamical friction not being active. So you see what I've done so far. I've looked at various of these systems and tested for the presence of dynamical friction in terms of is there evidence for this. And in every case so far tested, the evidence is negative, which means it's a consistency argument. It's not like we are saying it works here and it doesn't work over there. It's everywhere a failure. So it's a consistency argument. And so this can only be the case if there are no dark matter halos. And here's now the final test, the dual dwarf galaxy theorem, which was proposed some time ago, but now actually for the first time verified. In any cosmological theory, there exist primordially formed galaxies and tidal dwarf galaxies. In the standard model of cosmology, the primordial dwarf galaxies are dominated by dark matter, and tidal dwarf galaxies have no dark matter. Okay, so this allows you to explicitly test directly, essentially, for the presence of dark matter, but this is an argument independent of dynamical friction. That's a very different argument. And so here's just a reminder, this is the simulation, this is with dark matter, that's why these two galaxies merge. But you see that in this simulation, this tidal tail forms these new dwarf galaxies. And these dwarf galaxies are called tidal dwarf galaxies because they're formed out of tidally expelled material. And we know that these do not contain dark matter because they are so low mass that they cannot capture dark matter particles. Here, the formation is turned the other way around in the sense that first the galaxy forms from stars and gas, which would then have to capture dark matter. And in a cosmological setting, so these galaxies before the encounter, these big galaxies, they form from dark matter. First the dark matter forms and then the gas falls in. So here, first the gas forms the galaxies and then maybe dark matter could be captured, but because the dark matter particles are moving too quickly around here, they can't be captured by these dwarf galaxies. So we have galaxies with dark matter, those are the primordial galaxies formed after the Big Bang, and we have galaxies without dark matter which form in these tidal tails. And here's an observation. You can see that's exactly what we observe. And there are many other cases. So this is very well documented in the real sky to work. What we find is that at the same baryonic mass, they must have different radii because the primordial dwarf galaxies which form in dark matter halos So first you have the dark matter halo, which then collects the gas to make the galaxy. That's a different physical process than if you form a galaxy naked without dark matter. You don't have the dark matter to help you gravitationally to collect the gas. It has to do it by itself. The consequence is that these two types of galaxies must have different radii. The ones are much smaller than the others. Yeah? And this is verified, falsified by the data. Observationally, we do not see any difference whatsoever in the radii, as if dark matter doesn't exist. They all look the same, these galaxies, whether they formed tidally, so they are young, or whether they formed primordially, so they are old. This indicates indeed that there is no dark matter. Therefore, all the galaxies obey the same law of gravitation, and they don't, so that their structure is only given by the way they form, which is just the gas dissipation when the object forms under self-gravity, rather than with the help of dark matter. And so this independent test verifies the previous conclusion: dark matter does not exist. Dark matter does not exist, so the cosmological model would be ruled out. Yeah? And here is now an interesting result or publication from last year. Parallel to this, and without, I did not know Václav Vavričuk, who's working in Prague, but suddenly his paper appeared in Monthly Notices, and he showed, he just calculated that assuming the model is correct and the first galaxies form, then these first galaxies produce so much dust, because the stars, when they form, they produce dust. And the dust heats up through the radiation of the stars and re-radiates in the infrared. And this is something we know extremely well from the Milky Way, from every other galaxy. All galaxies radiate primarily in dust, in the infrared. That's where they are most bright, because galaxies are full of dust. And so these first galaxies would have made a huge amount of dust. And he just showed that by the calculation, if you integrate all the photons which come to us from the first galaxies which are forming, then you basically get the CMB, the cosmic microwave background. And the problem is that the Planck measurements, or the analysis of the CMB, has not taken this into account. Essentially, the situation is such that if you would take this into account, what he calculated, you have to subtract the cosmological dust emission from the background, CMB background, and nobody knows what you're left with. Basically, it seems, according to this calculation, you'd be left with 0, which means that the most holy argument for a Big Bang in terms of the CMB is now being questioned. And unless one can show that this is a wrong calculation, and so far this hasn't happened, this statement stands and it has to be worried about. So either we can show, or somebody can show, that this calculation is wrong and Planck stands, or if this is not wrong, then Planck falls, and we cannot use the CMB to argue in favor of a hot Big Bang anymore. So this is the conclusion 1. I should be ending, right? Yeah. So it seems the observed universe does not contain dark matter particles. And by implications, the standard model is not the correct description, and the observed universe appears to be more regulated, have more symmetric structure than expected. So I will not continue now, but there is a second part which contains the steps one now can do to actually achieve a better description, and there is quite a lot of research going into that direction. So thank you for listening. Yeah.
Could you say me, of course, you can say that, could you say me, if you don't want to have a dark matter, because some people who are working in this subject, for example, Milgrom, also does not want dark matter, and he has additional theory called Mond theory, modified Newtonian dynamics. It's a modified Newtonian dynamics on the level of small acceleration, which is of course unmeasurable on the Earth, absolutely, but it is possible that this theory is modified. And from this theory, using only one constant, he is able to fit very many galaxies. I think maybe all galaxies under consideration. And the cosmological model is too far away from this theory. It's some kind of different dynamics. Secondly, I could say that you said that Einstein theory or Newtonian theory is used for a very long distances. But I have a theory, we have a theory, which was used also on very long distances, or from small distances to very high distances, and which is very correct. It's electrodynamics. Electrodynamics and its quantization is a very good theory on short distances and very long distances. That this argument, I think, does not work, short and long distances. Okay.
So I didn't quite. Going on from this conclusion, of course, the obvious thing now is to actually look at other gravitational theories, yeah? And whatever one can come up with, one should test. So we are currently indeed working with MONDs. This would be the next material. We are now capable in Bonn to calculate a cosmological model in MOND as well as galaxy formation. And this looks extremely positive, actually. MOND seems to be working remarkably well, but we are testing MOND just as rigorously as the standard model of cosmology. So we want to see if we can falsify that approach. And any other approach apart from MOND, of course, is just as important, and one would have to test it. But I'm not sure I understood that last point of your you have a theory of gravitational of quantized gravity, or which one?
No, this is
Yeah.
But you said that this gravitational theory was used from short distances to very long distances. For example, Newtonian or Einsteinian general relativity. But electrodynamics, which is a very good theory on very short distances and very long distances. Then your argument that we cannot extend gravitational theory from short distances to very long distances does not work in this case.
Yeah, no,
Probably gravity also is in this.
Sure. But so the argument I was bringing was that the Newtonian theory, which is the classical form of Einsteinian theory, which classical means we can also do calculations with it, is based on empirical data restricted to the solar system. So if we want to apply it to larger scales, it's an extrapolation. But I did not say it's not allowed to do that extrapolation. One can do the extrapolation, but one should not be surprised if it doesn't work. Yeah? And so.
You presented a very specific argument, because I guess the strongest one of yours was this based on the galactic dynamics and the dynamics of small group of galaxies. Mm-hmm. Now, it seems to be very straightforward. And could you just comment how common is this conclusion? I mean, are all groups of galactic dynamicists agree on the points which you presented, or not? And if not, then why?
That's a sociological question, and I already indicated this, because if you remember, I showed the M81 group, and there were two research groups, the one from Korea and the other American one, which published papers, but only conference proceedings, coming to the conclusion that they cannot reproduce the observations with dark matter, but they could without dark matter, but still within Newtonian dynamics. And so interesting is that these papers were never published as refereed papers, but both independent groups got the same results. And so the question is, why didn't they continue? Because 1999 was when they stopped, and after that nobody ever looked at that group again, although it's the nearest group to us. We have very good data. So the question is, why does this not happen? And that is, I think, a really remarkable question which sociologists and philosophers will have to answer. Why do the modern galactic dynamicists, why are they not using these data or studying these data to come to such conclusions? In the community in which I'm part of, I know that Mond is rejected. Yeah? There's a very strong sentiment about Mond not being correct. This is also being taught at universities by professors, and I don't understand why that should be the case. I've myself experienced in the United States at a table that we were discussing, this was well before I started with this research, that somebody mentioned Mond and another researcher jumped away from the table and just left because one doesn't discuss that. Yeah? The question is, why is that happening? Yeah? So maybe you can answer that as well as I can. One can only speculate why physicists are so opinionated. I cannot understand it because I'm not married. It's not like I think Mond is correct and dark matter is ruled out. Most of my research was with dark matter. I didn't think it should be wrong, except that my research showed me that what I'm seeing in the computer with dark matter doesn't match what I'm seeing out there. And what am I supposed to do as a scientist? Just ignore it? Of course, I can't ignore it because we want to understand how nature works, and so we have to continue beyond dark matter if it doesn't work with dark matter. And why the majority of astronomers are not doing this? Well, that's really a sociological question. It's about, so I know from my students, Pawlowski was one of my students. He also obtained later a Hubble Fellowship, so he was very successful as well as some other of my students. But I know from these people who have dared to enter this field and continue research on this field that it is very poisonous. So these people had, when they were still much younger, they had senior researchers tell them that they should stop working with me, that they should stop working on Mond, or they can write a paper on Mond, but only to show Mond is wrong, nothing else. And there's a very strong such feeling. I know from students who have been discouraged by the community to not work on these topics because it is wrong, or whatever the argument was. But there's a very strong peer pressure in the community to criticize the existence of dark matter and then to also work on other on alternatives. Now the question to you is, why is this happening? That's something you can answer maybe better than I can.
If you consider, the global warming, I would know the answer, but I cannot see, frankly, the reason about cosmology.
Well, it must be something to do with belief, yeah?
I don't think so. It's known that Mond can describe well rotational curves, even in different galaxies, but it's also known that it cannot describe collisions of clusters or some other, or CMB evidence for dark matter. So can you comment on that?
Yeah, sure. So,
perhaps also gravitational waves, if possible.
So it's often stated that Mond has been developed to explain rotation curves, but it's actually not true. I mean, the motivation for Milgrom's idea were rotation curves. In the late 1970s, that's when the first evidence came up that the rotation curves are flat. And so Milgrom was at that time working in Princeton, and he considered what sort of dynamics would you need to explain this. And today we refer to that as space-time scaling invariance. There seems to be some sort of symmetry. Other note under Mond. Now the thing is that from the 1980s, where this was formulated, after that a large amount of data came, which were not in the theory. And every single observation has been verified, including galaxy clusters. And now I want to mention the bullet cluster, which many people will think is a proof of dark matter and a disproof of Mond. And this is now coming to your question about why the community is not following these arguments. The bullet cluster is a perfect example because when the bullet cluster was discovered, it was immediately reported that shows dark matter is there, it excludes Mond, and the public relation activity was immense on this. It was later shown that actually that the bullet cluster works in Mond and does not work in dark matter. But you don't know about this, right? Why don't you know about this? That's my question. Because, of course, you don't read the technical papers because you can't. Obviously, one doesn't have enough time to follow absolutely everything, so that's completely understandable. The problem, however, is that in your minds, you've been made to believe that galaxy clusters don't work in Mond. That's what sticks because the reporters tell you so. And you do not know that there's a lot of scientific activity and research papers have been written which actually show exactly the contrary, including lensing. And this is now the question to you. You've asked the question, why is the majority not following these arguments? Well, my question is, why don't you, as members of the community of physicists, don't know about the research which has shown that Mond actually explains these systems much better than dark matter? Let me explain to you the bullet cluster. The bullet cluster is two very massive clusters, very massive, yeah, which have just went through each other, and the gas content. So most of the mass of a galaxy cluster is composed of dark matter and gas. The galaxies are nearly insignificant, and so when these two structures collided, the gas dissipated, leaving the shock front. And from that, one can calculate the velocity of these two clusters when they had to collide. The velocity is about 2,000, 2,500 kilometers per second before collision. And that's where the problem lies. You first of all, in the cosmological model, you have to have enough time to grow such clusters. I mean, a galaxy cluster of the mass of 10 to the 14 solar masses doesn't just form. You need a lot of time for it to form. That's already a problem, to actually form such massive clusters given the time the universe has. The other problem is that given that the universe assumes isotropy and homogeneity, all the matter initially is moving away in the Hubble flow, right? So you first have to have two regions which are nearby to each other, which are overdense, which follow the Hubble flow, then decouple from the Hubble flow to then make the galaxy clusters, which then have to attract each other, to fold through each other, and then separate. And the universe is not old enough to do this. Can't do it. Why don't you know about this? But everybody uses the bullet cluster to prove or to argue there's dark matter. And now you can do the same calculation in Mond. And in Mond, it works wonderfully because in Mond, effectively, so the way Mond is known today, effectively, if you assume there was a hot Big Bang and you have the structure formation, because Mond is effectively a stronger gravity, these things form much, much quicker. And because it's a strong gravity, you get the gravitational pull, and you form these clusters easily. And then you do the lensing in Mond. Of course, you have to use the relativistic formulation. That's something one then can ask: do we use the Bekenstein TVS formulation, something else? But the calculations which have been done, and they are non-trivial. There are a few people in the world who can do this. The calculations which have been done on the bullet cluster have shown that it works extremely well. So you look at the weak lensing structures in a Mondian gravitational framework, and the calculations are consistent with the Mond methods of these clusters. That you can apply this to many clusters, so most of the clusters are working well in Mond. There is some evidence for a stress, so in the sense that there seems to be somewhat more gravitational force than you would just calculate, but if you look at the history of how a typical galaxy cluster forms, in the center of the galaxy cluster is a huge elliptical galaxy typically, which would have formed with an incredible star formation rate, so thousands and thousands of solar masses per year, which forms very quickly right at the beginning. We know today that the stellar population which forms in these type of objects is highly different to what we see in the Milky Way. It's very biased towards massive stars, leaving a lot of black holes and neutron stars, which is like dark matter. And so this is something we're now working on. If one now takes a galaxy cluster in Mond and calculates the mass distribution of the galaxy cluster, knowing that the stellar initial mass function changes with conditions, we do get a very significant amount of additional dark mass in these clusters, which are just dead stars. And so this seems to be indicating that in Mond, galaxy clusters are much more natural and easier to understand than in lambda CDM, where you have the problem I mentioned with a bullet cluster, which actually is an argument against lambda. Actually, the bullet cluster by itself falsifies lambda CDM with a high significance. I'm not sure if it's 5 sigma, but it's pretty high.
So attempts to modify the theory of gravity have been with us for a very long time. There have been many attempts to modify the theory of gravity in many, many ways. Formation of galaxies is just the one experimental observation. We also have other observations like gravitational waves, like both observation of gravitational waves, but also observations of systems that emit gravitational waves and slow down in their rotation. We have the structure of the CMB, fluctuations of the CMB, and many other things. And do you know a modification of a theory of gravity that passes all these experimental tests?
Yes, well, no, I don't know any single such theory which does all of that, but one has to be a bit careful with this. So gravitational waves are obviously a strong empirical constraint on any gravitational theory, because in any gravitational theory has to be must allow the propagation of gravitational wave. Now, Mond, I'm not sure about. I have not looked at that in detail. One would have to ask Milgrom. As far as I know, Milgrom, he would not say that this is in contradiction with Mond, but it depends on what one does with Mond. Is a classical theory. It's like asking, is Newtonian gravitation consistent with gravitational waves? And that question doesn't work.
Well, I'm asking for a modification of Einstein and gravity.
Well, and that's now this is an interesting question. Do we come to the question of what is gravitation? Okay, is it a space-time distortion or not?
Well, it's just a question of having a theory with which we can quantitatively predict observations, and it would reproduce the observations as the Einstein theory does.
Well, Einstein's theory obviously does not reproduce the observations.
In the case of that you have described, it doesn't, so long as we believe the simulations. However, in the case of gravitational waves, it does.
So the if Einsteinian field equation is not valid, given these arguments, we have a number of options. One option is to say it is valid, and what we are seeing is a departure from the equations of motion because of additional effects. And those additional effects might be quantum vacuum. So Milgrom actually wrote in 1999 a very interesting paper where he pointed out that if we take the quantum vacuum into account, then the Unruh radiation from the vacuum in the limit of flat space-time actually leads to the Mond effect. Okay, so this is a possibility. Nobody knows whether this is true, but it suggests that maybe Einstein's field equation is completely valid, but in the extremely weak field limit, we are now seeing additional effects from the quantum vacuum. This would be very nice, because this would immediately explain, keep gravitational waves propagating everything. So this is one possibility. For us, if we want to understand the dynamics of the universe and how galaxies form and evolve, we have to have something with which we can actually do calculations, and in that case it would be Mond, because Mond would take effectively into account this vacuum effect. Because you basically have this transition from the Newtonian gravity in the classical limit to the region where the quantum vacuum might have an effect on motion. So this would be very, very nice. That's one possibility. Another possibility is that Einstein's field equation is just one mathematical formulation, which is very successful in a particular limit. In the very strong field limit, it's doing very well. But that it's wrong. It's not the correct description of gravity. It's quite possible. And if you can look at Verlinde's suggestion that gravity is an entropic, arises from an entropic principle. So you have differences in entropy, which then, because one then interprets to be the force of gravitation. So that's Verlinde's suggestion. In which case, gravity would not be a distortion of space-time, but something completely different. One might still use similar equations in the end as in terms of working on a day-to-day basis, but the origin of gravitation would not be a space-time distortion as according to Einstein. So that's another possibility. That possibility one should continue to research. in order to maybe at some point get a final description of gravitation in that framework. It's possible gravitation is something entirely different. It might actually be something yet different, which is again an emergent phenomenon. It's not actually a force, but just emerges because of the properties of particles in space-time. Yeah? So, you know, what you said is absolutely correct, but it's not so easy to just write down a theory of gravitation. If you think it's a space-time distortion, you've already limited yourself to the possibilities. Absolutely, yeah. Yeah.
We can have many qualitative ideas, but at some point we should test them quantitatively.
Exactly, yeah.
And so long as we have no alternative that works quantitatively, we should not. I mean, we should test one theory that has quantitative prediction against another theory that has quantitative prediction. I think we are making this mistake here, that we are testing a theory that gives quantitative predictions against qualitative ideas that may be this way or the other way, or, you know, maybe yes, we should make these tests, but...
I have a following point. There have been papers showing that certain galaxies have normal Newtonian rotation curves, while the original evidence was that the sample of galaxies studied at that time by Rubin et al. Had all these flat curves. And now you mentioned in the middle of your talk that from your simulation, there is a possibility that certain galaxies will have normal curves and the other will have flat. Yeah. How it works with you?
Well,
excuse me, the question was to the lecturer. Excuse me, please. Pavel.
Yes, from observed galaxies, we know that in massive galaxies, the inner region is always Newtonian, and that is a problem for dark matter because they have to argue that the dark matter is pushed out somehow and makes a big course, so the inner region is always Newtonian because that is observed. The outer regions then typically show the flat rotation curves or some other anomaly, like if it's an elliptical galaxy, you might find a constant velocity dispersion or so on. But a galaxy which is purely Newtonian has not actually been discovered, except one, which is maybe two. It's called the galaxy NGC 1052DF2 and NGC 1052DF4. And these galaxies were discovered last year by, or shown, they were known before, but they were shown by Van Dokkum et al. That they appear to be completely without dark matter, essentially without dark matter. So they're actually dwarf galaxies, which seem to have no dark matter, and this was then used to argue that therefore dark matter exists because if you have a gravitational framework, so if you have like Mond, then all galaxies should show a dark matter effect, yeah, because you can't switch off gravity. So all galaxies should be Mondian and should always have evidence for dark matter, but it wouldn't be dark matter, it would actually be Mond. And they found a galaxy without dark matter, therefore disproving Mond. So that was again out in the press. The Nature paper was written with those statements in there. Now remember, a Nature paper, in order to get a Nature paper accepted, first the editor has to think it's interesting to pass it on to the referees. That's where most papers already fail. Then you have 3 referees who go through the material and check it. Okay, and in that paper there was a statement that it essentially rules out Mond. So the question now, and this goes back to your question, how was it possible that this statement entered into a Nature paper, which supposedly publishes the best research, and that statement is completely wrong? And you have 3 referees plus the editor checking this, and none of the experts in Mond were asked. How is that possible? Now, this is basically the question to you again. Why is the community reacting like that? Yeah? Because in a sensible scientific environment, you would have said, okay, we found this evidence, this galaxy seems to be a problem, it doesn't have dark matter, therefore it should be a problem for Mond. Let's ask the Mond experts, Milgrom, Famé or Megoch are the 3 leading Mond experts. They could have also asked me. Within an hour, they would have gotten the reply that this galaxy follows exactly the prediction of Mond. Why? Because Mond, by not being a linear theory, has this, what is called the external field effect. So basically means that if you have an isolated galaxy, it generates around it a potential, which, if you interpret this from Newtonian eyes, looks like a dark matter potential. If you put another galaxy nearby to it, this dark matter halo disappears. And because it's not a linear theory, so the forces so the gravitational force between two objects depends so the inertial mass remains the same, but the gravitational mass changes depending on the distance. Yeah? And this external field effect can be calculated. They haven't done it. They chose to suggest Mond is ruled out, which then went out in the press, so everybody thinks Mond is wrong, but they made an error in the calculation, and if you now look at that paper, there is now a brief communications arising with me as first author. We will point out that that statement is wrong and how to do the correct calculation. Yeah? And so it's true that if you would find an isolated galaxy, which is far away from any galaxy, and it is purely Newtonian, then this would completely rule out Mond.
Okay, I shall take a liberty to ask a following question, following your statements. Can you make a very short list of experimental observational facts which are in sort of a tension with Mond? You mentioned one, you said there is certain stress with one, but is there any more which you know of? But very short, really. And then I would also ask, if it is possible, ask astronomers for a short comment.
So, okay, so a list. So the galaxy clusters have some stress in the sense there could be additional matter, which, however, I think we can nicely understand through the formation of these stellar.
Yeah, this is what you mentioned already, but something else?
So the hardest test invented for Mond was actually in my research group in Bonn, where we argued that if Mond is valid on all scales, it should be valid in star clusters, which are far away from the Milky Way. And so we predicted the motion of the stars in some of these clusters, and they've been measured, and they've been shown to be in tension with Mond. But, and there's a big but, yeah? So one can then continue discussing this, but this is another thing.
Okay, now just a short list.
Other than that, there's nothing I know of which really is in severe tension, in the sense that I would say, I'm finished with this line of research because it doesn't work. Just like with dark matter, for me that's finished. I wouldn't continue that
Okay,
at all.
that is optimistic.
But
yeah.
one can propose tests.
Definitely one should.
So I don't know, I could mention 2 tests maybe. Should I or not? It's very short. The one test where we can test if Mond is correct is looking at white binary stars. So with the Gaia mission, we can now actually measure the motions of stars which are nearby to each other very precisely, and there are thousands of fairly close to us stars which are very, very separate but move together, so a binary star. And then if Mond is correct, there will be a systematic difference between the velocities. So this can be statistically tested for, and this research is ongoing right now. So some experts are now, including in Bonn, are now actually trying to see if we can rule out Mond or test Mond in this way. And the other one is the nearest star, Proxima Centauri, which is just about a parsec away. We know its trajectory. It's on an orbit around A and B Alpha Centauri. This is the next star to us. And Proxima Centauri is moving, and we can calculate that if Mond is correct, it should have a deviation of its motion over decades, which can be measured. And this is something which we are currently actually doing. So hopefully we will actually be able to make such direct tests.
I'm not sure about the Proxima Centauri. I haven't looked into that. I think the statistical studies with Gaia are feasible. What I'd like to ask you is, how far does it go? Suppose there is no dark matter. What are the next steps? I think that dark matter is, in general, something that we don't have a proof of, like you said. But then we have the dark energy. Does it go away as well? How does it go with the expansion of the universe? Do we get rid of it? Where does it end?
Yeah. Well, that's a very good question. So, if dark matter doesn't exist, then the whole model is invalid. Yeah. So the evidence for dark energy comes from the model. Therefore, we wouldn't necessarily we wouldn't be able to say there's any evidence for dark energy, right? Because the dark energy rests on the model being correct. Otherwise, we wouldn't have this problem. So it's quite possible if we would have a different model, we would have again dark energy. But this is completely speculative. it's quite possible that we would have a model which doesn't need dark energy. And in fact, there's indication that we have that already.
Okay, and so, then if we don't have dark matter and dark energy, is the universe non-flat?
Is the universe not?
Not flat? Is omega not equal to 1? Or we don't have to redefine omega?
The flatness in particular, I think a very strong argument comes from the baryonic acoustic oscillations, right? So the structures we see on the CMB, which we can interpret in terms of a flat universe only in that framework. But again, if the model falls apart, the thing is that if the model falls apart, we don't have a mathematical tool to calculate if we see an object at a certain redshift with a certain luminosity, we don't know which distance it is and we don't know which age it has because we don't have a model anymore. Huh? So that's the problem.
So do you also get rid of inflation?
Well, I mean, inflation is something very uncomfortable from a theoretical point of view, very uncomfortable, right? And so is it possible to have a model without inflation? Well, I have seen such a model, yes. The question is, can one transform that into something which one can test against the data? Yeah? So I could quite imagine that maybe we would have a model which doesn't need inflation, dark energy also not, but this is very speculative at the moment.
Okay, and finally, you didn't mention anything about the pioneer anomalies. Are they, do you think, consistent with the MOND or not? Or what is the current understanding of this?
Well, as my understanding is that recently it has been shown that the anomaly isn't there. So they've discovered that the spacecraft has some residual radiation, thermal radiation, which supposedly explains this anomaly. Yeah. So it's not an anomaly, yeah.
Okay, I suggest maybe, you still want to, okay. Maybe that will be the last question, and then everybody would be invited to discuss with Pavel.
My comment or question is after joining a seminar of former Royal Astronomical Society in Copernicus Center for 3 days, he explained his view on the cosmology and dark holes. And so I'm a stupid physicist, and I asked the question whether after 100 years we still can believe in the proof of general relativity given by Eddington, because I expected the original paper as an optical physics. He neglected the normal optical behavior of light, and then he proved the gravitational, say, bending. But upon assuming the neglecting normal optical behavior, he assumed that the solar corona consists of the neutral gases which are on the Earth. So this particular assumption was wrong. So on the point of view of experimental science, the assumption of Eddington was wrong. So still there is open question whether the sun was able to bend the light with optical properties of corona. So if scientific community is reluctant to check this basic physical property of light and matter, then still some questions should be open.
Yes. Well, so I think there should be, of course, calculated what effect does the plasma have on the propagation of the photons past the sun. But we do know that light is lensed from the lensing observation. If you have a galaxy cluster and it's massive, you can see very strong lensing features within the optical image of the cluster of objects which are beyond that. In fact, one can observe to much higher redshift by using galaxy clusters as lenses. So so lensing definitely works, and it seems to work in the strong field regime. Seems to work very much like Einstein, according to Einstein's theory. In terms of Eddington, well, I guess at that time one had to make those assumptions for the calculations. And it would always be interesting to redo the calculation for the photons to propagate through the corona.
Okay, thank you so much. We shall put a stop here, and everyone is welcome and to discuss with Pavel afterwards. Thank you so much once again.